Good morning, everyone. I hope I'm not too loud. My name is Ravi. I'm with Intel. I am an SSD solutions architect with Intel. I work specifically in the Optane team. Optane, I hope every one of you have heard about Optane. Optane is the latest and greatest in SSD technology. It's pioneered by Intel. It's a new technology, SSD technology, and you may be wondering why I'm talking about a block device such as SSD when the topic of the presentation is something to do with memory. And I promise you that I will definitely explain you how Optane fits into this whole in-memory compute ecosystem or in-memory compute area. Before I get there though, I wanted to, like I said, that's why I started with Optane, because Optane is the underlying hardware that actually powers Intel memory drive technology, which is the topic of my discussion today. I have my email, my Twitter handle, and my LinkedIn profile URL on the screen here. Please feel free to connect with me on those platforms. Just a legal disclaimer. So, like I said, I want to start with what we call as world's most responsive SSD. And let me give you an introduction to Optane and Intel memory drive technology, right? So SSDs have been there in the market for a while, right? And traditionally, SSDs have been based on NAND technology. And the way NAND technology works, because of the way NAND technology works, it's a comprehensive process to actually erase the data in a NAND-based SSD, right? So you have something like an SSD has sectors, multiple sectors constitute pages, multiple pages constitute blocks. When you write data into SSD, you will be writing in pages, but the way SSDs, the NAND-based technology works, it can only erase in blocks. So if it has to erase the data, it has to erase the entire block. It cannot erase the specific pages. So if your data has changed, right, it cannot go and change the data in place. So since it has to erase the entire block, and not all the data is still in that block, what it has to do is it has to copy the correct data or the good data into a separate location, and then remove the bad data. So for every erase cycle, there are multiple writes that happen, which is what is called as, that's why the SSDs in general are over-provisioned. So if you might have heard about this term called over-provisioning of an SSD. It's a very key attribute of NAND-based SSDs. Now, because of that over-provisioning, there is a lot of wear leveling that happens on the SSD because the die gets wear level over time. And because of that, again, a lot of processing is happening. The controller, the SSD controller, has to do a lot of processing behind the scenes because it has to be efficient enough, right? It has to determine what is the efficient way of managing this whole wear leveling process, which is also called as garbage collection. So all these different phenomenon happen in the background because of these attributes, the way NAND technology works, right? Optane, on the other hand, is a completely new technology. It is not based on NAND technology at all. It has no transistors. It is bit level addressable. So all the phenomenon that I have explained to you before about NAND technology, none of those apply to Optane, which means that there's no over provisioning, wear leveling, garbage collection, all that is out of the door. And because of that, there is no over provisioning, and the device itself is very highly endurant. If you think about it, right, NAND SSDs, I've told you that it has to, there is a lot of over provisioning happens, and because of that, the drive itself is not very endurant. If you look at the spec of a NAND SSDs, generally they are like 1 drive writes per day and something like that. Optane, on the other hand, is 30 drive writes per day. And that's exactly why I explained to you, is because of those phenomenon that don't exist with Optane. It's bit level addressable. It's a differentiated technology. Now, before I get into how Optane fits into this in-memory compute area and how it powers Intel memory drive technology, I want to touch upon key attributes of Optane SSDs that then if I tell you why Optane is good in these key attributes, you will appreciate later on that a fast device such an Optane SSD can certainly be used as memory, right? So I'm setting the platform here as to explain to you why some of the key attributes are very good. Optane is very good at some of these key attributes. Throughput, quality of service, latency, and endurance. So let me touch upon this key attribute called as queue depth, right? For those that are less familiar with the concept of queue depth is essentially the number of concurrent requests of data that you expect from storage at any given point of time. So the number of requests that are pending for the SSD device itself, that's defined by queue depth, right? So as you heard, so basically, most NAND-based SSDs are measured at their performance peak, which is like a queue depth of like 100 or over. So if you look at any specs of a NAND-based SSD, you will say that, okay, these specs are at queue depth 100 or queue depth 128, stuff like that. But if you think about it, real-world scenarios, real-world applications, queue depths are not that long, especially if you think about like database applications, cache, or log files and stuff like that. The queue depths are typically in the range of between 4 and 12. That's more like a real-world application scenario compared to NAND SSD specs, which always talk about higher queue depths. And there are use cases that fit into that category, but majority of the mission-critical applications fall into the low queue depth range of 4 to 12, which is a very exactly a sweet spot for an Optane SSD, because it performs very well in that low queue depths of area. If you think about it, a single file write in a synchronous mode, you get a latency of 10 microseconds, or sometimes even less with an Optane SSD. With NAND SSDs, you're talking about milliseconds in that range, but 10 microsecond is the latency that Optane device supports. So very, very, very low latency device, very fast device. And the other thing I want to touch base upon is what's often overlooked with this approach is, like I said, the enterprise applications, when they fall into that lower queue depth range of 4 to 12, and you have a device like Optane that's giving you low latency and best throughput at that performance, in that queue depth range. So throughput is, bandwidth of the SSD device is much higher, and the latency is much lower in that particular queue depth range. So what we are showing here is a breakthrough performance when you compare a NAND-based SSD in a real-world mixed workload. That's another key thing I want to stress upon, right? If you think about, if you look at some of the specs of NAND-based SSDs, they're generally talking about either 100% reads or 100% writes. Again, that is not typical in an enterprise, especially mission-critical applications, right? They're usually mixed read-write. And a more ideal scenario is a 70% read and 30% write. So majority of our specs with Optane SSDs that we have, that I'll be showing you at least, they're all in that, we take that mixed 70-30 workload and with that lower queue depth range. So what you see here is at that low queue depth, the blue bar and the orange bar. So the blue bar is the Optane SSD, and the orange bar is the the orange bar is the if you see, the orange bar is SSD DCP 4800X, that is the Optane SSD, and the blue bar is the NAND-based P3700, but it's also using a 4K block mixed read-write of 70-30, 70 read and 30 writes. Sure.
It looks like your graph's flattening out, so where is this going up?
The curve of the knee, you mean?
I'm just asking, when you go up to 100%,
Yeah, queue depth of, so if you think about analytics writes, or if you have a lot of sequential reads or writes happen, that at that queue depth range, there's no doubt about it, right? NAND SSDs are much better. If you think about like, completely 100% sequential, 100% writes or 100% reads. What I'm saying is Optane fits very well in that mixed read-write workload, 70-30 workload, which fall under that 4 to 12 kind of queue depth range. That's where Optane really shines. But if your workload is 100% read or 100% write, and mostly it's sequential writes, then there's no doubt your NAND-based SSDs are better suited for that kind of workloads. This is another key attribute I want to touch upon, right? Predictably fast service. So if you see the orange bar on the bottom of the chart, that's where it's actually the quality of service, right? It's always consistent, as opposed to the rest of the NAND-based SSDs plotted all over the chart. But if you see the consistency of an Optane SSD, because especially if you think about it, the 99th percentile range, right? 99 and whether it is 99.99 or 90.999, those kind of percentiles, Optane really shines. If you look at those tail ends, if you look at the numbers for tail for NAND-based SSDs, that you will see a lot of differentiation between NAND and Optane SSDs. And as far as the numbers, like up to 60 times better, especially at that 99 percentile QoS. Again, going back to that point, right? Optane is ideal for critical applications with, where you have, when your application is latency driven, right? Absolutely, Optane is the best fit. But if your application is more like, like I said, sequential reads or write, 100% writes or reads, bandwidth oriented, your NAND SSDs are better. But if your application is latency driven, Optane really shines. Mm-hmm. Yeah. Yeah, so if your application, if you're doing 100% reads or writes, it's usually determined by bandwidth more than latency, right? If you have a SQL, if you have a lot of concurrent sessions, SQL queries running, but they're all read queries, then that's not a real fit for Optane. Because like I said, if you have 100% reads or write, bandwidth-oriented, NAND SSDs would perform better. But in a more typical real-world scenario where you have, because especially if you think about like these applications that you have heard about in keynotes, right? The HTAP or HOAP kind of applications, hybrid transactional analytics platforms, right? You have, the whole point of HTAP systems are that you have OLTP and OLAP on the same platform, right? So you have a lot of ingest happening, you have a lot of transactional data coming into the platform. At the same time, you're doing a lot of analytics on the same platform. So that's a mixed read-write workload. And we actually have, we work with a company specifically in that HTAP area, and we have noted down the performance, like the performance of Optane SSD in that mixed read-write workload when you have like data ingestion happening, and there are like a bunch of SQL queries analyzing on the same data set. As the data is being ingested, it's being analyzed and stuff like that, right? So on the same platform. Those are the kind of areas where Optane really shines. And endurance is, like I mentioned before, it's a very key attribute, right? And endurance of SSD, of an Optane SSD, is why it is practically suited to be on memory. You may have heard about Apache Pass, which is basically Optane technology on the DIMM form factor. That's not what I'm covering here, but just to tell you about how endurance is the technology, if it's going on a DIMM, that tells you about how endurant the device itself is, right? So because of that, so you have, as the number shown here, 30 drive writes per day. That's like 2.8 times more total bytes written at the similar capacity of a NAND-based SSD. So that's the kind of endurance that the Optane device provides. Now, I'm going to be showing you some numbers here. I wanted to show you Intel memory drive technology, but not just talk about it, but actually show you some numbers that I have benchmarked myself, right? So to set the platform for that discussion, I want to I want to tell you about what my problem statement is and what I try to achieve from this exercise, right? I wanted to optimize in-memory processing engine like Spark, take it and optimize it in such a way that I get better performance out of my Spark application, but for much better cost-effective solution. I want a cost-effective solution, but I want to get an optimal performance from my Spark application. That's the whole point of my exercise. And the key point is that I wanted to stay within the limits of the budget, right? Obviously, I can extrapolate the hardware, I can get more DRAM and stuff like that, but again, that's not what I'm here to do. I wanted to stay within the limits of my budget and yet get an optimal performance from an in-memory processing data engine like Apache Spark. For that exercise, I made some assumptions based on my own experience, having looked at the Spark deployments at enterprises and also talking to customers. I looked at what is a typical Spark deployment infrastructure. I took that, a scaled down version of that, created that in our lab. So I took a 4-node cluster, I created that in the lab, and that's what I used to actually benchmark Apache Spark. I actually also looked at the system resources, generally what is the kind of memory and the storage that they use in the Spark applications, and I tried to stay within the same kind of range. So my cluster, actually, I'll show you my software and hardware configuration in a little while, but it has 192 GB of memory on each of my nodes. Like I said, I have 4-node cluster. I use 1 as a management node and 3 data nodes for the Spark application. And also, I actually wanted to come up with a representative workload, right? What is a good representative workload for Apache Spark? Now, clustering or classification is a very common algorithm used in a lot of machine learning and Apache Spark applications. So it has its use cases in like fraud analytics and customer segmentation, stuff like that. So it's a very good algorithm. That's a common algorithm that is used. So I said, okay, let's take a workload that represents something like a classification or clustering algorithm. So I actually took K-means, which is a very one of the oldest and most commonly used classification algorithms out there. So that's what I took for running this workload. And also at the end of it, I'm going to show you the 2 different solutions and how each one fits into a different kind of usage model and explain to you the benefits of each of those. This is a quick overview of the K-means workload straight from Wikipedia. Like I said, it's one of the most commonly used, oldest and most commonly used algorithms. The way it works, the K-means works is it happens in 2 steps, but it's an iterative process. In the first step, it actually assigns the set of observations. It takes a mean of your new observations, and it tries to correlate with the newest mean of all the clusters it has, which is the closest mean, and then it assigns the new observation into that cluster. But then in the second step, it actually recalculates the mean of the cluster, because now the new data, and because of that, the centroids have changed. And this happens in an iterative process until there is no change to the it has converged, basically. The algorithm has converged. That means that there are more changes. The means is not changing. That means that that's the end of the process. So it's an iterative process. It happens in 2 steps. There are few steps in K-means that are more CPU intensive, and there are a lot of steps which are memory intensive. So the whole reason I took K-means is because I wanted to have a workload that's more memory intensive. Obviously, we're talking about in-memory computing, right? So that's the reason I took the K-means workload. This is my hardware and software configuration. Like I said, I have 4-node cluster. It's the homogeneous cluster in terms of both CPU and memory and everything else, except the storage, which is different from the management node. I don't need additional storage because I'm not going to store any data over there. Data nodes, I use 3.7 terabytes Intel P4500 SSDs for input data set. That's where I'm storing the input data set. And I'm actually using 2 375 GB Intel Optane SSDs on each data node, right? And I'm using these Optane SSDs in 2 different ways in the test cases that I'm going to show you. In one of the test cases, I'm actually using the Optane SSD as a block device, as an SSD. And I'm using it, as you know, Spark if it cannot fit the data set into memory, it starts spilling to the disk, right? So I'm using a fast device like an Optane SSD in that test case. And then in the other test case, I'm actually using Optane SSD as memory. Now that's, again, you might be thinking, like, I'm talking about SSD, which is a block device, and I'm saying it's being used as memory, right? Maybe it doesn't make sense. So let me give you an introduction of Intel memory drive technology. Intel memory drive technology is a software product. It sits at the virtualization layer below the OS. It's a small piece of software, but it's an intelligent software. It's a machine learning software. And I'll explain to you why it is intelligent also. But what it's doing is, when you have, before the OS comes up, when you have Intel memory drive technology, what it does is it actually updates the BIOS tables, the memory maps, and it uses the addresses of your SSD and presents it as a single large pool of memory to the OS. So if you have, let's say, 128 GB of DRAM in your machine, and you have a couple of Optanes of 375 GB Optanes that I have, for example. So when the OS comes up, it doesn't see the block device anymore. It doesn't see the SSD anymore. It just sees 700 plus memory available to the system. So from that perspective, there is no change to the OS or the application. There's no change at all, because the device was taken over by Intel memory drive technology, and the memory maps updated. So this is a very key point to note, that you don't have to change anything at the OS level, at the application level, or even at the higher programming interface level, because the way they interact with the memory doesn't change. From their perspective, there is no change. You don't have to change anything in your code to either use DRAM or use SSD. It's not like that. You just use your memory the way you have been using, but underlying IMDT takes care of managing that data between DRAM and SSD device. And even for Intel memory drive technology to work, it actually needs a little bit of DRAM. We're not saying that you have completely eliminated DRAM, because what it does is, and this is why it's called intelligent software, it's using DRAM as cache. And it is using the high bandwidth and low latency device, a fast device like high endurance device like Optane, and its data is actually sitting on Optane. So if there is a cache miss, if the data is not there on the DRAM, it fetches from the SSD and puts into DRAM, right? And it's intelligent because what it does is it tries to detect patterns. So there are two different. I'm going to be digging a little deeper into in the next slide that I'm going to show you, but that's what it does. That's why it's an intelligent software. It's leveraging the throughput, the bandwidth, and low latency of a device, and that's exactly why I've shown you that Optane is very good in those key attributes of latency and throughput, right? And some of the usage models for Intel memory drive technology is that you can grow beyond your system DRAM capacity. So you're not limited, your server is not limited anymore by 3 terabytes or whatever DRAM capacity you can have. If you have more PCIe slots, because Optane is, at the end of the day, it's a block device. It's a PCIe, NVMe PCIe device. So you add more PCIe devices, and now you have, voila, you have like 20 terabytes. You can go up to 20 terabytes or even higher, up to 28 terabytes in a single machine, and at much lower cost compared to DRAM. So that's the key benefit that you get out of Optane. Again, like I mentioned, there is no change to the software stack, no change at the Linux OS or the applications or the programming layers, no change to the hardware, runs on bare metal or loaded from OS before the BIOS. And two different usage models, right? You can either expand your limited DRAM capacity. Like I said, we go beyond your 3 terabytes of limited DRAM capacity, or you can actually displace DRAM. You can have, like, if you have, let's say, 350 GB of DRAM, you can actually go lower, get only like, we have a recommended set of values, right? Depending upon how many Optane devices you will want to use, we can give you a recommended value of DRAM, how much DRAM capacity you should have, right? So it can displace DRAM or you can extend DRAM. So this is where I would like to touch upon the intelligent piece of that software, right? the way it works is, so I'll give you a simple example. For example, if you're running a simple query, select first name, comma, last name from so-and-so table, right? When you run that query, IMDT behind the scenes, it's trying to detect the pattern. Next time when the same routine runs, it knows that this routine would require, let's say, 200 or 300 KB of data. Why? Because first name and last name are fixed data types, right? So it can do a prefetching. It can go to the SSD, get the data ahead of time, that's the pattern matching, and put the data on the DRAM. So for the application, it's still coming, it's, there is no change. It thinks that the data was sitting in the memory, but it wasn't. But IMDT behind the scenes has taken, based on its intelligence, it prefetched the data from the SSD device, from a block device, into DRAM. And that's how it makes it faster. So what I want to also mention here is that there may be cases where IMDT may not be a fit, right? Obviously, DRAM is the fastest thing on the system, right? There is no way you can go faster than DRAM. But if you have a use case that is more like very, like I said, it fits into that category of prefetching and pattern matching, you can get much better TCO by having more memory, especially if you need more memory for your applications. You can have this is a better cost-effective alternative, right? That's what I'm trying to show you here. So the first, that's a probability-based memory access pattern. Now, there may be cases when maybe the workloads are not that sequential kind. Maybe they're very random, right? There is no pattern matching. Will IMDT work in those cases? Yes. And IMDT would work in those cases if the workloads are highly parallelized, which again fits into that it's a good use case in a lot of big data and in-memory applications, is because they're highly distributed and parallelized. And how IMDT works actually in those scenarios when it cannot do a lot of pattern matching is, again, it being an intelligent software, it works very closely with the CPU. If you have a highly parallelized workload, right, the overall performance of the workload is what really matters. It doesn't matter how long it took for individual tasks in the workload. So if a task needs certain data, which is not there in the DRAM, what IMDT can do is it works closely with the CPU. It can tell the CPU to go to the next task in that parallelized workload while it can go and fetch the data for the previous task. So at the end of the day, it will make the CPU efficient by switching between the tasks. It doesn't have to wait for the data that was not there. It can go continue with the other CPU task while IMDT go and fetch the data. So if the workload is highly parallelized, it can still give you a good performance benefit. And there are other cases which are very specific to high performance computing workloads, where the workloads are more CPU intensive. So you might have heard about this whole NUMA balancing, right? Non-uniform memory access. You have cores, the CPU cores, the memory bank, which is closer to the CPU. It always helps if the data is closer to the CPU. So IMDT can benefit in those cases, and it can bring the data closer to the CPU, which again is a specific, it's a very good use case. That's why we have a lot of good use cases that we have demonstrated, especially in the high performance computing area. Now I want to go to the actual benchmarking exercise that I've done and show you the numbers and the value of IMDT. And like I said, my workload is Kmeans workload. First, what I wanted to take was take a baseline scenario where I run a workload that actually fits into DRAM. So I took a smaller workload. If you see on the left side, that's the configuration of my Apache Spark application. And on the right side, you will see on the top right corner, you will see the CPU utilization chart. And on the bottom right corner, you will see the memory utilization chart for every workload. So you can see the difference between the different workloads and how the CPU and memory being used in those specific workloads. So in this case, it's a 1.2 billion samples K-means workload, and it fits entirely into memory. There is no IMDT here yet. It fits entirely into DRAM. I have 192 GB of DRAM on each of my data nodes, 3 data nodes, and the time taken to run the workload is 5.3 minutes. The CPU utilization, the CPUs are very underutilized. There's a lot of scope for CPU there. Memory is completely utilized. So as you can see, this is a very important thing, right? I want to take a workload that uses a lot of memory, because obviously I'm talking about IMDT being used as memory. Next, what I did was, for the same exact workload, I actually added IMDT now. Now I have two Optane devices with IMDT, but what I wanted to show here is, just by adding IMDT, nothing changed, right? So the data set is still the same. It fits into memory. So although I have more memory available now from IMDT, it's not being used yet. So if you see the memory utilization chart, the CPU utilization, memory utilization is very low, because there is a lot of memory that's being unused. Because now I have, like, instead of 192 GB of memory, I have 750 of memory on each of the nodes because of Optane and IMDT. But it's the same workload, it's not using it. And if you see the CPU utilization between the previous one, mm-hmm. Mm-hmm. So exactly, right? There is no change. From the application perspective, I don't have to worry about whether it is using DRAM or SSD. That's being done automatically by IMDT. Your application doesn't have to say, okay, I have to put this data into DRAM instead of SSD. You don't have to do any of that. Automatically, IMDT takes care of that, getting the data and make sure that as much as possible, it will be in the DRAM. It uses DRAM as cache. Mm-hmm. There is no DRAM available. DRAM was the same. I didn't change anything in the DRAM. I have 192 GB of DRAM. Now I have two Optane SSDs. So now I have 750 GB of memory pool. It's not DRAM. It's overall memory pool is 750 GB. And DRAM is still the same, 192 GB. So you'll get a better picture when I go to the next workload with IMDT, right? So as you can see, nothing changed in the CPU utilization in terms of the previous chart and the next chart. So the CPU utilization here, that's the data set that fits entirely into memory, and similar CPU utilization, nothing much changed just because of IMDT. And the time taken to run the workload is again exactly 5.3 minutes to the dot. So one of the key things of Apache Spark is that you will have to, you can configure a lot in Apache Spark. You can configure your number of executors, the amount of memory that you have assigned to each executor, the amount of CPU cores you have assigned to each executor. Lot of configuration changes, but all those configuration changes are per workload. If you want to get better out of your Spark performance, you have to tune your Spark configuration a lot per workload. So imagine you have, the workloads are not static, right? They change all the time. I mean, if you just have one kind of workload, yeah, sure, it makes sense. You just to spend some time on it, tune your Spark configuration, and be done with it. But majority of the enterprise applications, that's not the case. You have lots of variety of workloads. Either you have this option. You either spend a lot of time configuring your Spark for every workload, or you have a better alternative, something like you can throw more memory at your Spark application, because obviously more memory it's good for at least most of the Spark applications. Obviously, it's an in-memory processing engine, right? So because more amount of time spent on configuring your Spark means more time to market, right? And time is money always. So in this case, what I still wanted to show you is I still spent some time and tried to fine-tune my Spark configuration and get better runtime out of it. So I actually was able to get a better performance. Before it was 5.3 minutes. Now I got to run it in 4.5 minutes by changing some of those attributes that I've highlighted in the chart in the box above. So I gave number of executors is 30. And I actually increase the number of cores per executor, because, like I said, in the Kmeans workload, there are some stages which are more CPU intensive. So those stages got accelerated. and I got a better performance. But I still have to make sure that the other stages, which are more memory intensive, they should not slow down. So I had to make that balance between cores, memory, and executors and come up with that ideal configuration that will give me a better runtime. And I had to tweak a lot of times, go do a lot of trial and error, and I came with this configuration that gave me a better performance of 4.5 minutes. Now, if you see the CPU utilization and the memory utilization, pretty much same. CPUs are still underutilized. There is a lot of CPUs left there. I didn't leave it there. I further tried to configure it, right? If you think about it, it's a little bit counterintuitive because now I have reduced the number of cores to 5 and I got a better performance. So that's what I'm trying to show here. It all depends upon your workload, right? Spark configuration for each workload, you can spend a lot of time and say, okay, this is the thing that will work for this workload. But then you will have to spend, all that, repeat that, all that exercise for the other workload, right? It's not something that you can keep spending time on. But I still wanted to show you, you can still do it, right? If you want to do it, you configure your Spark more and you can get better runtime. And in this case, I actually got 4.1 minutes. So that's the best performance I could get for this particular workload by tweaking a lot of performance configuration parameters. So now I said, okay, let me take, this is my representative workload. Now I took a bigger workload, larger workload, it's almost more than double, 2.2 billion samples of K-means workload. Now it's not linearly, it's not linear, right? If you 1.2 billion and 2 billion, the data set size is not linear because the way K-means works is works in different stages and the input data set for each stage changes because it's always recalculating, right? It's an iterative process. So the input data set keeps changing all the time. So I took this workload, I know it doesn't fit into memory, it's much larger workload. I took that and it ran in 43 minutes with DRAM. I just have 192 GB of DRAM. All right. Now, either I could repeat that same exercise that I did with the other workloads, where the smaller workload, tweak all the parameters and try to come up with a better runtime for this. Or, because I have more memory available at my disposal, I said, let me just work with a standard general configuration of Spark. What is general guidelines that any Spark developer would follow? For example, right? Number of cores should be either 5 or less per executor, and you just take amount of memory that you have in your infrastructure and just divide it equally among all the executors, right? Just standard guidelines, and I just ran it with IMDT. Now I have more memory. Obviously, if you see, the memory utilization is much higher now. It's using all the available memory, and the runtime I got is 12 minutes compared to the baseline 43 minutes. Obviously, it had less memory, but 43 minutes compared to now I have more memory with no configuration, no much time spent on configuring anything in Spark, and I got 12-minute runtime. But if you see here, the CPU utilization, the CPUs are still underutilized. There's a lot of scope for CPU. But before I get to the next stage, I want to show you the solution economics of the benchmark that I ran until now. If you think about in terms of TCO, what benefit did I get by using IMDT? I added 20% to my overall infrastructure because now I added 2 IMDTs, two Optane SSDs with IMDT per data node. I had 3 data nodes, and that increased the overall cost of my infrastructure by 20%. And the performance, runtime performance I got as an improvement of 3.5x. That's almost like 72%. So that's a key factor there. 20% added cost to the infrastructure gives me 72% runtime performance. Now, I was telling you about looking at the CPUs, right? The CPUs were still very underutilized. Now, this is another kind of potential benefit that I wanted to show you. So what I thought was, my workload is good. I got a better, by adding 20% cost, I got 72% performance, but my CPU resources are still underutilized. Why am I having those many CPUs if I'm not using them? So I said, okay, let me try to do this. Let me try to maximize the utilization of my resources, right? So I actually removed a data node. If you see my configuration now, it actually has only 2 data nodes. So I actually removed a data node altogether from my infrastructure. I have 1 management node and 2 data nodes, same exact memory and everything. And I ran the same exact workload. And now it ran in 30 minutes. Now if you see, the CPUs are almost choked. So I'm completely utilizing all the memory, all the CPU resources. I'm utilizing my infrastructure to the fullest extent possible, right? Now if you see, the 30 minutes is the performance that I got. Let's look at the solution economics of this, right? What I have is, what we are talking about is, I have baseline that ran in 43 minutes. When I added 20% overall cost to my infrastructure, I got 72% improvement in performance. I actually reduced the cost of my infrastructure compared to the baseline where I had 192 GB of memory. I actually reduced my infrastructure cost because I removed a data node, and I still got a performance benefit of 30%. That's a key factor there. So if you have workloads that are CPU, underutilized CPUs, you can actually go with having IMDT and maximize your resource utilization and reinvest your dollars in maybe higher core count CPUs, right? So there are 2 different usage models that I wanted to show you here. As an alternative, this is an informative slide. I wanted to show you, if you were to add the same amount of memory that I got from Optane, if you want to add using DRAM, if you just buy more DRAM and increase your hardware, then what will the cost be? Obviously, I did not have that kind of DRAM to use on each of my data nodes, so I didn't run the workload, but actually I can show you at least the cost, how much it would cost you. So the cost benefit would be 40%. Now if you think about it, you increase your overall cost by 20% and you got 72% of performance. Now if you increase your cost by 40%, what is the performance gain you get? So that's something that you can work with or not. That's the use case. So I'm presenting to you what I have shown you, and if that works with the workloads, and if that's, that cost benefit is better, which I assume will be for a lot of enterprises, it's a very good alternative. So key takeaways, right? Reduce the manual optimization. You don't have to spend a lot of time configuring Spark or any other in-memory centric applications. You can use more memory at lower cost and maximize your CPU utilization. And like I showed you, for workloads that are having underutilized CPUs, you can actually increase the CPU utilization. And like I said, maybe reinvest those dollars into higher core count processors or whatever other benefits that you may get. Just some resources for you if you want to learn more about Intel Optane or Intel IMDT. You can go to those websites. And I also have a technical brief I published using Intel memory drive technology on a more micro benchmark called as Terasort. You can look at those also in the paper that have the link on the screen here. That's the end of my presentation.